In this video, we're going to discuss and show you how to calculate different measures of central tendency, including the mode, the median, and the arithmetic mean. We have a companion video which gives you more examples of how to calculate these statistics by hand and using different kinds of spreadsheets and SDA. But for now, let's go ahead and start looking at what measures of central tendency are and how they work. One of the nice things about measures of central tendency is we all have a pretty good idea of what they are. We're pretty familiar with measurements like your college GPA. Now, admittedly, this is not a straight arithmetic average. It's a weighted average, and therefore it's a little more complicated. That is, this is an average weighted by your credit hours or quality points, but it does give you a sense of what an overall average is. It's a measure, a single descriptive statistic that describes a location in a distribution that's defined as being somewhere near the center, and therefore it's believed to be typical. One of the averages that I spend a lot of time looking at, because I'm a hockey fan, are goals against average, which is the number of goals a goalie lets in for every 60 minutes, which happens to be the length of a game. I like this statistic because, if you have little kids who are playing 40-minute games, you can adjust this to be an average over every 40 minutes or per game. A measure of central tendency is really a single number that attempts to describe numerically the center of a distribution or a group of data. And because we know we have different kinds of variables, we have our discrete and our quantitative variables and non-orderable and orderable variables, we have different kinds of measures of central tendency taking into account the relative lack or relative fullness of numerical information in our measurements. Going from least numerical information to most, we're going to discuss the mode, the median, and the mean. And then finally, we're also going to discuss a special kind of mean, which is a weighted average. And then our last topic will be to discuss percentiles. The mode is a particularly easy measure to interpret. It's simply the category or value of the group that contains the most cases. So looking at the bottom, we can see we have a frequency distribution of race in 2008 based on data from the General Social Survey. Our three categories are white, black, and other. And just looking at the frequency column, we can see that the most frequently occurring value is white. And that's therefore our modal category. Our average person in the General Social Survey is white as measured by the mode. Shifting over to the right, we can see an example taken from the National Institute of Drug Abuse, and it measures whether a person has tried any of these drugs in the past 30 days. Ignoring that top bar which says illicit drugs, which is simply the percentage of people who tried any of those drugs, you can see that the biggest column is the one labeled marijuana with 18.1%. Therefore, marijuana is the modal category or the average drug used by people in the United States in the past 30 days. Now, this is a different kind of average than you may have seen, and the reason we like the mode is that we can't calculate an arithmetic average here because marijuana, psychotherapeutics, cocaine, hallucinogens, and so forth don't have numerical quantities attached to them. They're simply non-orderable discrete categories, and therefore we have to use a measure of central tendency that's appropriate for that kind of measurement, and in this case the mode is it. We can also talk about the modal religion in the United States, and we can see that the modal religion in 2012 was Protestant, followed by Catholic, followed by none, and followed by Jewish. So again, that's a non-orderable discrete measure. Sometimes we have group data, and again, it's this notion of having these labels attached to them. So a group frequency distribution displays the numbers of cases with the same value or score. And again, all we need to do to define the mode or to calculate the mode is find the category with the most frequently occurring score. And in this case, that's the American South if we look at population by region. What if our data aren't grouped? What if we have raw data? So here I have values of y sub 1 through y sub 12, 12 observations. And they have the values of 5, 3, 8, and so forth, down to y sub 12 equal to 6. To calculate the mode for these data, the first thing I'm going to do is create a little frequency distribution. So I'm going to take those raw numbers, those values, the 5, the 3, the 8, and I'm going to put them into a sorted order and then create a little frequency distribution so that I can find the most frequently occurring score, which happens to be 6. When you have a small data set like this, one really nice thing to do is to create a stem and leaf plot. And I'm going to refer you to our examples video where you can see a fairly lengthy description and example of how to calculate stem and leaf plots or how to create them on your own. But they're a great little back of the envelope kind of calculation that shows you the distribution of these numbers, as well as making it easy to identify the modal category, which again in this case happens to be 6. Here I've taken the age of people in the General Social Survey based on year 2000 data. And I've created a frequency distribution, and you can see that it's not grouped. There's one bar for each year. We can see here that the mode is 32 years old. That is, there were 77 cases, or about 2.7% of this distribution fell in the category labeled 32, and I've highlighted that with the red column. You can see one of the disadvantages of the mode when you have ungrouped data or lots of categories is that really there's a lot of modes in this example. Why aren't we choosing a value closer to, say, 38 or 39 or 40, 41, 42? All of those values are very close to the height of the column for the 32-year-olds. So that the mode, while technically being 32, could realistically have been any of those other numbers. So at some point, we need to move on to a different kind of average that takes advantage of the numerical quality of our data. A variable like age, in this case, while it's technically discrete, I have one column for each year, and it's orderable, but it is also a quantitative or continuous variable or measurement because we can measure the distances between the age groups. And therefore, we can take advantage of different measures of central tendency. The next measure of central tendency we're going to look at is the median. And the median is a single score or value or category that divides a distribution exactly in half, where by half we mean half the cases fall below the median and half the cases fall above the median. There are some tricks to calculating this, but at the end of the day, if you look at a frequency distribution and you use the cumulative percentage column, you can identify the category that contains the median value. And either you're done at that step, or then you can interpolate within that category to find an estimate of the median value. And that's how you get to this particular average. Again, quantitatively, this particular measure, while it's measuring the middle or center of the distribution, it's doing it with a particular rule or thought, which is half the cases fall below the median and half the cases fall above the median. By the way, there's another statistic to describe this particular measure, and that's the 50th percentile, something that you're probably familiar with from different kinds of test scores. Here's an example taken from a British journal called Lancet. It's a medical journal. And there they've did a survey and measured how many sexual partners people had in the last 5 years. They've created this bar chart. I'm not a big fan of this particular bar chart. I think the 3D is a little misleading, and I could do without the shading in the background. But nonetheless, it's a good set of data for these purposes. And we see two things. First of all, this distribution is skewed. That is, there's a long tail to the right and a short tail to the left, and it's kind of bunched up towards the left side. So here we have a positively skewed distribution. And when we have a positively skewed distribution, our two measures of central tendency, the median and the mean, will not necessarily be equal to each other. And we'll talk about that a little bit more in a minute. What that means is that these two measures might provide different answers, and in fact they do in this case. Look at the column, the blue column for women over the number 1. You can see that happens to be the median number of sexual partners for women. You can see that the average number of sexual partner for women is 2.4. So one measure of an average, one average provides a value of 1, one average provides a value of 2.4. Which is the correct average to present? Well, it depends on the shape of the distribution. When distributions are skewed like this one, typically the preferred measure is the median because it's not affected by extreme scores. By extreme scores, we mean all those scores, the 5 to 9s, the 10 pluses, in the tail of the distribution. Sometimes it's just best to present both of them and a visualization of the distribution so that your readers can make their own decision. But just be aware that if you use these two measures, median and mean, they may provide different answers. Here's another chart that I like quite a bit from the Census Bureau. I could do without the green color, but beyond that, here we have trend lines. So we've got one dimension which is over time. So we can see what's happening with average income over time. They're also showing us medians, not as an average, not averages, not arithmetic averages, because the distribution of income is highly skewed. So again, when we have skewed distributions, we tend to prefer the median. To provide a little additional information, they've broken out all these medians by racial and ethnic group. And then they've color-coded the timeline to show us where there have been recessions. And you can see that right at the beginning of those recessions, you start seeing a downward trend in household income, median household income. And then a little bit after the recession ends, you start seeing an uptick. So I like this chart quite a bit. If you're interested in the economy or inequality and so forth, it's a great, and a recession. It's just got a lot of information in it, very well done, and a nice presentation. So let's go ahead and look at a variable we've looked at in class called SEX-FREQ, sex freq, which is this sexual frequency in the past year. Over on the left-hand side, you can see the number that's coded in the computer in red, 0 through 6. And you can see the associated label. 0 is equal to not at all, 1 is equal to once or twice, and so forth, all the way down to 6, which is 4 plus times per week. Our next column is our frequency column, and it has the number of people who chose each of those responses. And then I've calculated the valid percentage, and then a cumulative percentage. To estimate the median for this example, we can use that cumulative percentage column and read down it until we come to the first number that exceeds 50%. For example, 22.3% of all the people responded that they hadn't had sex at all in the past year. We know that can't be the median because half the number of people have to fall below that value and half above. Well, 78% fall above and the remainder fall below. So that's clearly not the 50th percentile. Let's move down a row. 29.9%, nearly 30% of the sample, had sex once or twice or not at all in the past year. That is, it's 22.3 plus 7.5 is about 30%. Again, we haven't made it to the median because we have 30% below once or twice and 70% above. But if we keep reading down that cumulative percentage column until we get to, in this case, 56.6, we can see that that's the first interval, the first response that exceeds the 50th percentile. And just reading across the table and making a quick estimate here, I'm going to conclude that the median sexual frequency per year is about 2 to 3 times per month. Note that I didn't use the value 3, which is the number stored in the computer, because 3 has no meaning except to the computer. To us, it's the 2 to 3 times per month. What if we have raw or ungrouped data? Well, the median case is defined as the middle value or the middle case of some set of values arranged in order. So if we have an odd number of cases, and we sort our cases from low to high, our middle case will be equal to n plus 1 divided by 2. If we have an even number of cases, there really is no single middle case. There's 2 middle cases, and we're going to define our median as falling halfway between those 2 cases. Let's look at an example to make this a little bit clearer. Here I have a listing of corporations that and their corporate interlocks, their interlocking directorates. I've sorted them from high to low. So the corporation with the greatest number of interlocking directorates is Equitable Life Insurance with 75. followed by Morgan Guaranty Trust 72, Chemical Bank of New York 70, First National Bank 69, and Chase Manhattan Bank 66. I have 5 cases, so I have an odd number of cases. 5 plus 1 is 6, divided by 2 is 3. So the third case is the median case. In this example, when somebody says, what is the median number of interlocking directorates for these 5 corporations, the appropriate response is 70. Now, we talked about how the median and the mean are affected differently by extreme cases. What if Equitable Life Insurance didn't have 75 interlocking directorates but had 75,000? You can see that if we calculated an arithmetic average, Equitable Life Insurance would pull the average towards that big number. But in this case, we're calculating the median, which is based on relative ordering, and the median is not changed at all. That even if my numbers were 75,000, 72, 70, 69, and 66, my median or my average would still be 70. I've added in an extra case here. New York Life had 61 interlocking directorates. So now I have 6 cases. I have an even number of cases. Notice that there is no middle case anymore. I have 2 middle cases, 3 and 4. Once I identify those 2 middle cases to find my median, I simply take the arithmetic average of their 2 values. So 69 plus 70 divided by 2 is 69.5. My median here is 69.5. And again, like the example before, because we're calculating the median, this statistic is unaffected by extreme scores. If Equitable Life Insurance had 75,000 interlocking directorates, the median would still be 69.5. Sometimes our data are grouped into a table already, and we'd like to be able to estimate the median from the values of that table. You can see here I've laid out my apparent limits. These are income limits for a sample of 189 individuals. My apparent limits go 2,000 to 2,900, 3,000 to 3,900, 4,000 to 4,900, and so forth. I've also listed my true limits, which you'll remember are half the gap added to and subtracted from each of the apparent limits, half the gap between my apparent limits. 1950 to 2950, 2950 to 3950, and so forth. The column labeled with the small italicized f are my frequencies, the number of cases within each interval. The capital F is my cumulative frequency column. And then the cumulative percentage column is the column I'm going to use to identify the interval that contains my median. Now I've highlighted it here in red. And how do I know that my median falls somewhere between $5,000 and $5,900? I look at the cumulative percentage column and I read down and find the first number that exceeds 50. It's not 8.99, it's not 22.75, it's not 42.86. Again, half the cases are not below 4,000 and 4,000 to 4,900, and half the cases above. But somewhere between 5,000 and 5,900 is a value such that half the cases fall below and half the cases fall above if they were ordered from low to high. If you look at the formula at the bottom, I can tell you that I have 189 cases. If I can find the value attached to the 94.5 case, 94.5th case, 0.5 times n, then that's going to be my median value. So our trick is to find out what value is of that case. Let's move on to step 2. Within this interval of 5,000 to 5,900, I have 51 cases. I don't really know how those cases are distributed throughout that interval of $1,000, but I'm going to make an assumption that they're distributed equally. So if that interval is 1,000 units wide, in this case $1,000, and I have 51 cases in it, that means I should have a case every $19.61. The first case is right at the true limit, the true lower limit, and then I count up $19.61, and there's my second case, and then I move another $19.61 through the interval, and there's my second case in the interval, and I do that 51 times, each time moving $19.61. Well, here I've isolated the interval. I have my lower true limit, 4,950 at the left, and I have my upper true limit, 5,950 at the right. And I have a $1,000 interval there, and there are, in theory, 51 tick marks. I didn't put 51 tick marks because it made the graphic a little too crowded. I know that I have 81 cases below 4,950. Well, that's just the cumulative number of cases up to the interval that contains the median interval, the median value, but not that interval itself. I know I have to go to the 94.5th case. So my first case has to be 81, 82, 83, 84, and I can just count through this interval until I come to the 94.5th case. I have to count in 13.5 units. That is 81. I start at 81, I go to 82, 83, 84, and eventually I end up at 94.5, and you can see that it falls between two values. Now, I can do a little math to make this easier. I know I have to move 13.5 units through the interval, and I know that each one of those units is $19.61. So if I multiply those two numbers together, I know that if I start at 4,950 and I move through the interval $264.735, then I should be at the median value. And with a little bit of rounding, I'm going to define my median in this example as $5,215. So our steps again are to identify the interval that contains the median, step 1. Step 2, figure out how many cases are in that interval and distribute them equally throughout that interval. Step 3, count into that interval until we get to the median case and determine its value, and then add that to the lower true limit to get our median. We can do this with a formula. Now, this is our first kind of look at a formula that is formidable, but truthfully, everything in this formula just encapsulates those 3 steps that we just did. So let's look at this. Our P sub I is simply the median value of a percentile that we're interested in. L sub P is the lower true limit of the interval containing the percentile we're interested in. So again, thinking back to that table, we know that the interval that contains the value we're interested in has a lower true limit of $4,950. P sub I, the small p sub I, is the percentile we're interested in written as a proportion. Whenever we're calculating a median, we're interested in the 50th percentile, so we just plug in 0.5. N is the total number of cases, 189, and that gets us our 94.5. 0.5 times 189 is 94.5. From that, we're going to subtract C sub P, which is the cumulative frequency up to but not including the interval that contains the median. We know there's 81 cases in all the intervals below the median value. So 94.5 minus 81. F sub P. F sub P is the frequency of cases in the interval that contains the percentile. In this case, 51. And then finally, W sub I is the width of the interval. So looking at the formula a little bit, the part within the parentheses, the big parentheses, basically tells us the proportion of the way through the interval that contains the median we have to go to get to the median value. That is, 94.5 minus 81 is our 13.5. We know we have to count 13.51 cases into the interval. We know that the interval contains 51 cases. So 13.5 divided by 51 is the proportion of the way through the interval where the median lies. Because the interval is $1,000 wide, we're just going to convert that proportion to dollars. And so we multiply that proportion times $1,000, and then we add it to our lower true limit. We'll see this formula again when we work with other kinds of percentiles. Just remember, the median is the same as the 50th percentile, and this formula can be generalized to determine pretty much any percentile. We're going to move on to the arithmetic average now. So this is the average that people are most comfortable with and most typically calculate. You can see at the top that I'm beginning to use some different kinds of notation. And the notation here makes a distinction between statistics that are calculated on populations and statistics that are calculated on samples. More technically, in the kind of language I like, is a statistic calculated on a population is a parameter, something that's fixed and doesn't change. A statistic calculated on a sample is an estimate of a parameter or a parameter estimate. So I prefer that terminology, parameters and parameter estimates. We know that we are dealing with a population when we see Greek letters. So mu sub y stands for the mean of y based on a population. Mu sub y is a calculation of the parameter. And we might have variables like the average age, average sexual frequency, and we could refer to them as mu sub age or mu sub sex freak. On the other hand, when we're dealing with samples, we typically take our variable and put a line over it or a bar. And so we would say that we have y bar or the mean of y. And again, we might have age bar or sex freak bar. And we make this distinction between parameters and parameter estimates. This is going to come back and be important for us a little bit later in the course because mostly we don't have access to populations. We have access to samples. So what we typically do in statistics is we're making estimates of parameters based on sample statistics. Let's go ahead and look at the formula for the arithmetic average. We see that y bar is equal to the sum of y sub I divided by n. Now I've added subscripting notation there around that note, that summation sign, I equals 1 and n on the top. This says that we're going to set up a little counter called I, and that case, the first case in our data set, I equals 1, the second case, I equals 2, the third case, I equals 3, and we have some number of cases in our sample, maybe 1,000, then n equals 1,000. When you see the summation, what that's telling us is to start at I equals 1 and add up all the values 1, 2, 3, 4, 5 associated with those particular i's. Often, when I type this up for exams or if I'm working on the board or something in class, I leave the subscripting out and it's implicit. Other kinds of statistics, when we get into ANOVA, we're going to have to keep track of who we're counting, but for this arithmetic average, quite frankly, we're just going to always calculate it on all the cases in our data set. So that second formula, the one in the middle, is kind of a perfectly acceptable formula. Sum y divided by n. And then finally, you'll see in some statistics texts, people will factor out the n, and they'll use 1 over n times sum y. Just keep in mind that anytime you see this sigma, it means add up everything that comes after it. Now I've got some examples over here, but we don't have to spend a lot of time with this since you're very comfortable with averages. But for example, from the National Vital Statistics Report in 2004, the average life expectancy in the U.S. for men and women respectively is 74.5 years and 79.9 years. And then, of course, somebody has some made-up statistic, which is the average amount of time drivers spend kissing in their cars in a lifetime is 2 hours and 14 minutes. I'm not certain how they got that number, but I think I'm going to always present that one as an actual fact. When we looked at the median, and we defined the median as the center of a distribution based upon having half the cases below it and half the cases above it, we can define the mean in a similar way. It's also the center of a distribution, but in this case it has half the weight of the distribution below it and half the weight of the distribution above it. So you can see up at the top, I have a little graphic up there. Now when I was a kid, we called these things kind of teeter-totters, but really all this is a frequency distribution. And if you think of the fulcrum of this teeter-totter as being the place where the distribution is perfectly balanced, and I'm showing that with that up arrow, which is right at the number 11, that's your arithmetic average. Your arithmetic average is defined by having half the weight of the distribution to the left of the average and half the distribution to the right of the average. Perfectly balanced. You can see that I can calculate the arithmetic average over on the right, 2 plus 2 plus 8 and so forth, and I get a value of 11. And you can also see, we know that that multiplication is repeated addition, so I can shorten this a bit and just sort of use a little bit of multiplication, but I get the same value. You can now see why mean and medians do not always provide the same results when your distribution is skewed. If we added more cases to the right-hand side of this distribution, then our teeter-totter would begin to tip with the left side going up and the right side going down. And to find the balance of that distribution, the middle point by weight, the fulcrum would have to move towards those larger numbers. Similarly, if we added cases to the left side would sink, the right side would raise. And to find the middle of that distribution by weight, the fulcrum or the average would need to move to the left. So the arithmetic average is a good measure for us. It's what I call a democratic measure because every case participates, but it's sensitive to extreme scores. Every case participates, but some count a little more, the ones way out on the edges. Our median is not a democratic measure. The median is defined either by the middle case if we have an odd number of cases, or the two middle cases if we have an even number of cases, and all the other values are ignored. It's a uniquely or distinctively anti-democratic measure. But on the other hand, it gives us a pretty realistic idea of the middle of the distribution when extreme scores tend to bias it or change the number by pulling our mean towards it. Part of the outcome of this is that our arithmetic average has this unique characteristic that if we were to calculate the mean and subtract the mean from every case, this is something we'll do in a lot of statistics later in the course. That is, I calculate sum of y sub I minus y bar. So I calculate for each case, I subtract the mean from it. If I add up all those deviations from the means, they always sum to 0. What we will do later in the course is we'll calculate those deviation scores, but before we add them up, we'll square them. And that gets rid of the negative value. It doesn't change the property that these things sum to 0 if we don't square them, but we have this new property that the sum of y minus y bar squared is a minimum. And what we mean by that is that if we subtracted any value other than the mean plus 1, the mean minus 0.3, then we would get a number, a sum of all those deviations, and that number would be larger than if we had used the mean. Again, the mean is defined as the middle of this distribution by weight. The formula on the left is the formula we've just used for calculating the mean from ungrouped data. But sometimes our data are in tables or already put into groups. And so we have to use a weighted average. The only difference between these two formulas is the f sub I on the right-hand side. Some people use w sub I for weight. I like f sub I to remind me that I'm just weighting by frequencies. These two formulas are really identical. It turns out that the arithmetic average you've always calculated is technically a weighted average. You've just always set that weight equal to 1. Let's go back to our sexual frequency example. On the left, you'll see a red column that's marked from 0 to 6, which again, those are the numbers that are stored in the computer. That's how the computer keeps track of these responses. Attached to them are the labels that are useful to us, the not at all, once or twice, and so forth. And then in that first red circle under the y sub I, I've added a set of values that are going to be my estimates for each of those categories. Now, this is a little recoding, and what I'm trying to do is create a new variable that's quantitative and represents sexual frequency per year. So let's go ahead and take a look at the category labeled 4 or weekly. While the computer currently, in this SDA, currently believes that weekly is equal to 4, I can recode all the 4s to be equal to 52, which means once per week. Look at the category labeled 3, 2 to 3 times a month. Well, these people believe that they had sex on average 2 to 3 times a month. Is it 2? Is it 3? Is it 2.5? I'm going to select the value 3 at that upper limit of that response. And anybody who responded 3, meaning 2 to 3 times per month, will now be coded 36. So those values, the 0, 2, 12, 36, and so forth, are my new recoded values, and those are the things that I'd like to average. The next column, our frequency column, those are our weights. If the weights were equally distributed, or another way of saying that, if we had the same number of people in each response category, then we could simply average the y sub i's. But you can see that there's a lot more people who responded 0 than there are who responded once or twice, or 4+ times per week. So each of those values, the 0, the 2, the 12, have to be weighted by the number of people who chose that response. I'm laying out this table here and just pulling out the frequencies for each interval, and then these recoded numbers I'm bringing up. And what we're going to do is first calculate f sub I, y sub I. So if we look at the not at all category, we had 518 individuals who had sex 0 times in the past year. 518 times 0 is 0. Moving on to the once or twice row, we had 175 individuals who responded having sex twice in the past year. 175 times 2 is 350. Those 175 individuals had sex a total of 350 times in the past year. Of course, we know there's measurement error, but within what we've done with this variable and how it's measured, we're going to treat this as if that's real. I would go ahead and calculate all those multiplications, 262 times 12 is 358 times 36, and so forth. And moving down to the 4+ per week column, we can see we had 125 people who reported having sex 208 times in the past year, or 26,000 times. If I add up all of those product numbers, f sub I, y sub i's, I get 135,930. So one way we can think of this is I had 2,321 individuals who reported on their sexual frequency in this reporting year. Those 2,321 people had sex 135,930 times in that year. Some people having it less, some people having sex more. So I simply take the sum of those products and I divide by the number of people to get my arithmetic average of 58.6. After making this calculation, I can conclude that the arithmetic mean, or just the average, sexual frequency in the year is 58.6 times per year. Now you can see I've crossed out and showed you something you shouldn't do. I'll almost guarantee on one of our exams, somebody will take those values from before, those recoded values, the 0, the 2, the 12, the things that we're actually trying to average, and they'll try to average them. There's 7 numbers reported, and they'll just take those numbers, add them up, and divide by 7, and you can see that we get a value of 67. That would be a correct value if we had the same frequencies or same weights, same number of people in each interval, but we don't. Sometimes we have other kinds of tables that report averages to us, and we'd like to average the averages. So here I've used the General Social Survey to make an estimate of sexual frequency per year for heterosexual men, heterosexual women, homosexual and bisexual men, homosexual and bisexual women. We can see that 7,860 heterosexual men had average sexual frequency of 78 times per year, 8,836 women, the average is 76, and so forth. You might be tempted to look at that column of averages and average the averages, 78, 76, 65, and 75. Well, hopefully that big red X through that formula is warning that you shouldn't do that. We can't do that because we have so few homosexual and bisexual men and women that their values need to be weighted less than the other more dominant categories. So if we go ahead and do a straight arithmetic average of those averages, we find out that the average is 74. If we use a weighted average, so we take our 78 for the heterosexual men and multiply by the number of heterosexual men, the 76 times the number of heterosexual women, and so forth, we see that our arithmetic average, our weighted average, is 77. We have a 3 time per year difference, which is a pretty big difference if we don't use weighted averages. This would be similar to calculating your college GPA and not counting how many course credits you have. Now, as long as all the courses you have exactly 3 credits, or 2 credits, or 1 credit, or 4 credits, you could go ahead and just average your quality points. But since you've probably taken a mix of 1 credit and 3 credit and 4 credit classes, you need to weight your GPA. Same thing here. Don't average averages, use a weighted average. Well, what if we have a dichotomous variable? One of the things we can do with a dichotomous variable is recode it to be 0 and 1 for our two categories. Then we can just use our weighted average. And what we'll get is the proportion of ones. So the mean of a variable coded 0 and 1 is simply the proportion of cases coded 1. The GSS asked a question about whether marijuana should be made legal or not. And in 2008, approximately 40% responded legal and approximately 60% responded not legal. So I can calculate my arithmetic average for this variable as being 751, the number of people coded ones, divided by 1,247, the total number of people who responded, and there's my average, 0.6. Our last topic is to talk about other kinds of locational measures. Measures of central tendency are, at heart, locational measures. They point out an area of the distribution that's in the middle, whether it's defined as the most frequently occurring score, whether it's defined as having half the number of cases on one side and half on the other, or whether it's defined as having half the weight on one side and half the weight on the other. But we can pick other locations in our distribution and use those to gain an understanding of the distribution of numbers. Quantile measures are locational measures, and the ones that are most important to us are the two quantile measures, so that's our median. Sociologists tend to like quartiles, which are 4 quantiles. Economists tend to like quintiles, which are 5 quantiles. And then, of course, we have percentiles. And we can talk about percentiles and quartiles in the same breath. For example, the 50th percentile is the second quartile. The 75th percentile is the third quartile, and so forth. And, you know, here's a little weight chart for boys aged 2 to 20 years old. You've probably seen these in your doctor's office or on your medical chart. Your parents, I'm sure, have looked at them, and they track you by age, and they try to find out whether you're above or below average and how much above or below average, and whether you need more exercise or diet control or whether you need growth hormone. Okay? It just puts you into perspective with other people in your age group. Here's the formula for calculating percentiles, and it is suspiciously like the one for calculating the median. In fact, it's identical. The only difference between calculating the median and any other percentile is the p sub I in the brackets. So instead of substituting 0.5, which will always find the median for us, we would simply substitute the proportion of the quartile, or the proportion of the percentile that we're interested in. If we want the 90th percentile, we'd use 0.9. If we want the 25th percentile, we'd use 0.25, and so forth. Other than that, the formula is identical. So in this example, I've used the formula to calculate the 50th percentile, and that just replicates what we did before. We find the interval that contains the 50th percentile, and we note the lower true limit, and to that we add some quantity that gets us to the middle case. I also solved this problem for the 75th percentile, and that involves finding the interval that contains the 75th percentile, which we can do from cumulative frequencies, or we can do from cumulative percentages, and that value falls somewhere between $6,000 and $6,900. The only difference now is in the numbers that I put into this formula. I substitute 0.75 for my percentile. I substitute 36 for the number of cases in the interval that contains the 75th percentile, and I substitute in 132 for the total number of cases up to but not including the interval that contains the percentile. My width is still $1,000, and I get my estimate of the value of the income for the 75th percentile of approximately $6,221. Here's a picture of the distribution of income. You can see that it's skewed. It's positively skewed. And on the bottom, they have several of these quantile measures. We can see the median, which I've highlighted here. Everything in that box and below is below the 50th percentile. Everything above is above the 50th percentile. We can see the arithmetic average, which divides the middle of the distribution. And then we get our different kinds of quantiles at the bottom. Again, economists like quintiles, so they've divided this into the 20th, 40th, 60th, and 80th percentiles, which correspond to the first, second, third, and fourth quintiles. And then they've also put in the 95th and 98th percentiles. Again, a nice chart. It demonstrates or shows us visually that there's a great deal of inequality in terms of income. It shows us that income is skewed to the positive side because of the difference in the median and the average. And then we get these different quintile or quantile type measures, which indicate the percentage of people below particular values. It's a nice way of giving you information to put yourself into the scale to understand the distribution of income. I hope that helps you with understanding measures of central tendency, the mode, the median, and the mean. And if you have any questions, as always, please contact me or your TA, and we'll do our best to answer all of your questions.